what we've got today is we've got some electroplating going on. Shh, we don't want to scare it. Right. So what we've got a little battery, right? We've got some wires hooked up to it. And now on this side, we've got a copper wire coming in and a copper wire over here, and the electrons and magic and whatnot, right? So what we can see, maybe, we can see some bubbles coming up over here, just a little bit, and then there's like some metal starting to form right there, isn't there? There's metal. There's metal starting to form. I don't know what's happening. Seems like electrochemistry. We should probably investigate a little bit. So we're going to look at electroplating today, and then we're going to see how long it would take us to make like a lot of this tin. So what this was tin chloride, right? Tin 2, whoops, wrong part of the label. We've got tin 2 chloride, right? And now we're making it back into tin and chlorine gas. So that's what we're going to look at today. So if we want to do calculations around what we can do with this electromotive force and that kind of stuff, this is what we're going to do that, right? So there's a couple of different equations that are really kind of the same equation. So we're not going to work with worry about the derivation of it. So if you can see that in the book, if you are so inclined to do so. But we are going to use these equations a little bit. I'm taking up too much space there. So W being work, right? So the maximum amount of work. So we think about maximum amount of work. Well, we go back to the battery thing. Well, when that battery generates heat, that is waste energy. So that is work that will not get done. But if we do the maximum amount of work, all we have to do is do this. It's a negative Q because you're doing work, right? So that's why it's a negative. And E is going to be positive. So if you're going to do work, that's a negative because the system's going to have less energy afterwards and all that kind of stuff. So we have a negative Q times E, where E is our electromotive force, right? So the force of the cell, right? Your galvanic cell, the voltage of that galvanic cell. And if we multiply that by this Q factor, that's going to tell us how much work we can do. And Q is the coulombs of energy that we're dealing with. And that is the moles of electrons times this constant, which is 96,500 coulombs per mole of electrons. That is basically just taking the charge of one electron and turning it into a mole's worth of electrons, right? So if you take this 96,500 coulombs and divide it by the charge of, or divide it by Avogadro's number, you get the charge per electron instead of the charge per mole of electrons. But we typically deal with moles of them, so we've got a whole bunch to work with at once, right? So we can work a problem like that where we say, magnesium goes to Mg plus 2, salt bridge, Al plus 3 to Al. And we want to know if this runs until 0.33 moles of electrons have been moved, what's the how much work can you do with all that, right? So we need to figure out the electromotive force of the cell. We then know what our N is, our number of moles is 0.33. So we're going to take 0.33 times 96,500, 0.33 times 96,500 times the voltage of this cell. So for the voltage of the cell, I have magnesium going to magnesium plus 2 and aluminum plus 3 going to aluminum. So we go back here and we see those two. And I see Al plus 3 going to Al is a negative 1.66. So we go back here and we say, well, that was Al plus 3 going to Al, right? So Al plus 3 going to Al, so that's a negative 1.66. And then magnesium going to magnesium, or magnesium plus 2 going to magnesium, that's when we're going to have to flip. So we're going to do a positive 2.37 minus a 1.66, because the aluminum one is written correctly and the magnesium one is written backwards. So overall, that is going to give us a positive 0.71. If I multiply that by my 0.33 moles and my 96,500, whoa, where am I at here? Sorry, that was probably upsetting for your eyes. I apologize. So that gives us 31,845 times 0.71. And the maximum amount of work done would be 22,609 joules. You have volts for your electromotive force, and you have
coulombs, right? Where I've got to write it out on the board, but your units are going to work out on this. Something to keep in mind, I would write this down somewhere, is a volt is a joule per coulomb, right? So yeah, your volts, we change volts to joules per coulomb, and then we cancel out our coulombs, and we cancel out our moles with moles, and so all we're left with is joules on that, right? So 23,000 joules, basically 22,600 joules would be the maximum amount of work we could do with that. Any that got lost to heat or whatever, we would not get to do. We had already discussed spontaneity. I'm not sure why that's not spot in there. The book likes to act like this is a different equation. So we say, well, get free energy. Well, how are the units on energy related to the units on work? Well, the units on energy are the same as the units on work. Energy is your ability to do work. So then here's this other equation where you take NF, well, N is the number of electrons transferred, and F is the 96,000 coulombs per mole. And you say, and that's the max. Oh, so hey, yeah, this is just the same equation, right? This is your book acts. I don't know why people act like this is a different equation. It is not a different equation. Maximum amount of work is equal to your Gibbs free energy, right? That's what that's telling us. The electromotive force is in volts. Delta G is in joules per mole. Units work out, and everything is there. We'll go ahead and work a couple problems on the board on how you could do like weird things like this and like our magnesium chloride one and that kind of stuff, right? So we'll go ahead and switch over to that. So a common type of problem that we see with this, that students will have a little harder time with, is something like, it's the last one on the slideshow, but I didn't pop it up. But it's 10.5 grams of silver. How long would you have to run a 5 amp current in order to get 10.5 grams of silver plated on something, right? So there's a little bit of stoichiometry, and then this is kind of buried in the middle. So to me, I just usually do it as the whole problem is a unit conversion, but this is basically part of that unit conversion problem. So I'm going to do my 10.5 grams of silver to moles of silver. When in doubt, change to moles. So for silver, the molar mass is 107, I think. So for silver, the molar mass is 107.9 grams of silver for every 1 mole of silver. But I don't actually care about moles of silver. I care about moles of electrons. Here's the place where charge does matter. If I'm dealing with double the number of electrons, I'm going to have to do this for twice as long, kind of thing, right? So for every 1 mole of silver, it only takes 1 mole of electrons. That really gets me to my N part of this thing, right? But I'm just going to go ahead and keep doing this as a stoichiometry problem. For every 1 mole of electrons, it's 96,500 coulombs, right? We need to adjust this guy a little bit. 96,500 coulombs. Then we have our current, which is 5 amps. So if we go 5 amps, that's going to go down here because an amp, right? We saw that on the other slide over there. Maybe we saw it on another slide. An amp is a coulomb per second. That's what an amp means. Current is how much charge is going by per second. So like when you're in physics and you're talking electricity stuff, it's thought of as the flow of the water, right? If you compare electricity flow to river flow, it's how much water is going by. The voltage is like how steep it is, like how much force there is behind that and stuff. But we have 5 coulombs per second. So 5 coulombs for every 1 second. And that's going to give us our time in seconds. So 10.5 times 96,500 divided by 107.9 and divided by 5. And that gives me a big old time of 1,860 seconds, which if we divide that by 60 is 31 minutes. Right. So just a different way of kind of seeing an electroplating problem. I just kind of view it as a stoichiometry problem. Key idea there is an amp is a coulomb per second. Electricity units are goofy, and you just kind of have to get used to those doing that route. If we do a different kind of problem, knock off my 10 chloride one. Let's reset that real quick. So if we look at our tin chloride, it's been running for about 20 minutes or so now. And you can see there's some nice good sized tin crystals that have plated on there, right? The chlorine, for the most part, gets dissolved in the water and reacts with the water a little bit and stuff because chlorine's not real stable. Tin's fairly stable, so it can handle that. But another type of problem we could do would be to go the other direction. All right, I've gotten distracted and messed up. I'm not exactly sure what we had said before, but we're going to guess that there's 3.2 grams of tin that has formed there. And I'm going to guess that it's taken about 20 minutes for that to happen. I've got a 9-volt battery hooked up to it, but we don't really know what the resistance is, so we don't know what the amperage is going through that. And that's what I want to calculate. I want to say, well, what's my amperage, assuming I don't have any energy loss to other stuff, which I would, but I'm going to assume I don't. So amperage, right, is coulombs per second. So I know the time. I can pretty quickly figure that out. All I have to do is 20 minutes times 60 seconds, not divided by 60 seconds. And that is, of course, 1,200 seconds. So I need the coulombs of electrons. So all I have to do there is stoichiometry, right? 3.2 grams of tin. 10's molar mass is 118.7 is 10's molar mass. At some point when somebody was cleaning up my room, they stole my periodic chart, so I keep having to go and walk if there's one I don't know. So 10 is going from 10 plus 2 to elemental 10. So this would be, say, for every 1 mole of 10, it's 2 moles of electrons. Now, gosh, I got electrons and I need coulombs. I wish I had some sort of conversion factor to go from moles of electrons to coulombs. What is that conversion factor to go from moles of electrons? Oh, I know. That's that 96,500, right? So for every 1 mole of electrons, it's 96,500 coulombs. That gets me coulombs. If I take coulombs per second, that's amps. Look at this. You're learning about electricity. You're learning about Spanish the other day. I've made like 6 videos today. I'm way behind on stuff because of order things and whatnots. So we have 5,203 coulombs, right? Yeah, 5,203 coulombs. And we divide that by 1,200 seconds. And my average amperage has been 4.3 amps going through that solution. Assuming I've got 3 grams and it was actually 20 minutes, which I made all those numbers up, but who cares, right? Anyway, hope that works. Keep working problems in OWL and all that kind of stuff.